Hello guys, and welcome to another daily Leetcode challenge. Let's begin today's question 863. All nodes distant k in binary tree. It's a medium level question, and it goes as follows. Given the root of a binary tree, the value of a target node target, and an integer k, return an array of values of all the nodes that have a distance k from the target node. You can return the answer in any order. Okay, so quick summary in my own words is that I have a binary tree. I'm given a target node, and I'm given some integer k. I have to return all nodes that are k distance from that target node in the binary tree. Okay, let's confirm my self-explanation. I have an example of a binary tree, 351620874. And what is my k? My k is 2. I have to return all values that are distance k from the target node. Okay, 2 from here would be 7, 4, and 1. Output 7, 4, and 1 explanation. The nodes that are distance 2 from the target with value 5, the values are 7, 4, and 1. Okay, so right off the bat, if I was to think of this, I would probably, if I didn't know any other data structures, my thinking is, how do I traverse this binary tree in a fashion where I can keep track of some number such that upon hitting a certain value, that number would indicate that I am some distance away from the target node. Well, to a more maybe experienced person, you could see that maybe you could rearrange this tree in a fashion such that 5 happens to be my root, and then that level k is actually just level k is all the values that I would care about. So in this case, if I was to reorganize this tree as a tree where the root is 5 and all of my children nodes would be something like this: 6, 2, 3. The next level below that would be 7, 4, 1, and then level below that would be 0, 8. And it so happens to be that the level 2 of this tree is my response. So okay, the question now becomes, how do I create this this tree from binary tree? And so a binary tree has a specific structure where there's always only possibly a left or a right node. But here I can clearly see that, for example, if 5 was my root, I would have 3 children. So how does this even work? Well, a medium level question often requires you to maybe reorganize the input in a fashion that would fit your case, and that's exactly what we're going to do. So there's another form of tree that basically is a root to all possible children combination. It's also called a graph, and a graph is usually it could be done with a default dict. I believe that this is how you would do this. And yeah, now that we have a graph, the way that you would define this tree in the form of a graph is the key of this dictionary would be a value, and then the node, or the key would be the node's value, and the value of that key would be a list or a set, in this case, of all its neighbors. So how do we create this graph? Well, we can probably do a simple DFS. Let's define our DFS algorithm here. I mean, what would be the best way to traverse this? I would probably say node. If node left, I could have, if node left, I would say graph node add node left, and then I would also do left add node, and then I would call DFS on node left, and if node right, graph node add node. So all that I'm doing is mixing or matching up the root with the child, and then also the child with the root, and putting them into this graph. The result will be a fully populated graph that will actually have also overlaps. Let's call DFS on root. And okay, one more thing is I care about the values only, so let's put these values here instead of the actual nodes. And let's print this graph. Let's see what we get. We should be seeing a default dictionary print. We spelled print wrong. Print. We should be seeing a default dictionary where the default type is set, and here you go. Key and value is a set of 5, 1. Key 5. Value is 6, 2, 3. 2, 3, 6. Doesn't matter the order. 6 is 5. 2 is 5, 7, 4, and so on. Okay, perfect. So, yep, there's still some overlap. For example, 6 has a child 5. Or 6 is connected to 5, has a neighbor 5, and 5, where's 5, also has a neighbor 6. But for now, this doesn't matter. We can make sure to not ever go into a forever loop somewhere in our following algorithm. But now that we have created this structure of graph, essentially, all that's left for us to do is traverse it in a breadth first search fashion, and only stop at the level that we care about, only stop at k that we care about. And I've done a lot of BFS algorithm questions previously, so the structure of a BFS where you actually care about the level is pretty solidified now. We need two structures. We need a queue, and we need a temp queue. The queue is initially going to have the target value, and we also need, no, that's it, that's all we need. And while we have any element in queue, we would say that node is equal to queue pop, and we will say that, oh, we also need visited. We also need a visited maybe set that is initially empty, to make sure that here, when we are iterating over 5 and then looking at all of its neighbors, 6, 2, 3, when we're looking at 6, we don't accidentally add 5 back to it. So visited is going to get added to node, and then let's see. So now that we have visited, we need to populate this temporary queue that is going to be then basically describing our next level. So for, let's call it neighbor in graph node, we're going to say if not in visited, if neighbor not in visited, we're going to say temp queue append and neighbor, neighbor. Neighbor is already just a value. Okay, cool. So we've populated our next breadth essentially in this temp queue. Now, when do we stop iterating over our current level and look at the next level? Well, if not q, meaning that q is empty, we're going to say, we're going to say q is equal to, and this is a spread operator that is commonly temp used in Python. We can reset temp q to equaling a new array, and we can say k minus equals 1. So initially, if, for example, let's see, is k ever equal to 0? K could be equal to 0. So if 5 is the root in this tree, and we want actually the values that are 0 away from the target, we would return 5. But if we want 1, we would be returning the level below that. So we actually subtract k by 1. And now, when does this k become, when do we hit this time where k is a value that would indicate that we have to return something? Well, I think you could actually just say here, if k equals to 0, then we could just return q. Q is the current level that we're worried about. And as a final measure, if we ever have a situation where k might go beyond what we actually care about, and I think that is a possibility, then we would just return an empty string. Let's run this, make sure that this works. Temp q append. Nate is not defined. Nate. And let me remove this to make sure that it's clean. We seem to be running well. And yeah, this is a typical medium level algorithm where you're given a sort of like problem, you have to convert it into a data structure that you care about. In this case, there was two. It was a data structure and an algorithm that we had to do. And then do it. Let's see some maybe more. Let's see some other solutions. It seems like here they are. Still have a DFS to populate this. Oh, interesting. So it's a little bit different. It's a little different process for creating this. Oh, they're not creating a graph. Here they're not creating a graph. Here they are. So node parent, if not node return, node parent, parent. Interesting. What are they doing here? Are they restructuring the the tree? Target and then scene target. Okay, let's quickly look at this algorithm. This algorithm seems to suggest that if node is not being passed to it, then don't do anything. But then a node's parent, oh, it's appending a new. Yeah, this wasn't in the original. This wasn't in the original class of a node, so that's why maybe it's. Oh, and they all seem to be doing this. They have they're adding a new variable to the node. They're saying it's called parent, and then what are they doing? They have now that they have a parent, they're doing there's a specific even function, it does add a parent and then answer, and then visit it, and then for DFS, oh, so okay, so they're doing the exact same thing instead of though creating temporary a temporary data structure like we did in our case, the graph, and they're not actually doing BFS. Oh, I mean, they are to a certain extent, but they're going off and looking at the left, the right, and then the parent, and then they're okay. So very interesting approach. I would, I don't know. I think that what we did actually works completely fine, and it might even be a little bit cleaner if this function was here, because BFS was the topic for the previous sort of set of questions in Leetcode. But what they're doing here, in quick words, is what they're doing in the previous in the examples here is they're modifying the initial data structure, the initial tree, to have a backward facing node. So each node now essentially also points to its parent, and that way you can look at a target node and immediately know which 3 or possibly less than 3 neighbors you have. And then they're doing the same BFS except in a graph, and getting to those nodes that they care about. This is a perfectly fine solution as well, and it runs pretty fast. Let's see if actually we can beat some of these people. No, we can't. So okay, in any case, 76% is pretty quick. They're doing it a bit more in place, so that's why it's faster, but I would suggest using this as well. Feel free to copy, and have a good day. Please like and subscribe. I try to upload videos daily. Bye.